In this presentation, I'm going to give an overview of some of the work I've been conducting at the University of Dundee, looking at the design of buildings and infrastructure under extreme loading conditions. Now, there are many types of extreme environmental actions that our infrastructure and buildings may have to resist. One example shown in the top left of the slide is storm conditions offshore. So we're going to become increasingly reliant on offshore renewable energy moving forward. And these systems are placed far out to sea and need to withstand very severe storm loading, so waves and wind, and all the components of that system need to resist that. So that's the turbine, the mooring system, and also the anchors. We may also have extreme weather onshore as well. And this is particularly also influenced by climate change. So the image below, where we might have very heavy rainfall that can cause flooding and consequent problems such as landslips. And this can have a major effect on our transport network. And we perhaps know about that from a very recent example with the train derailment near Stonehaven earlier in 2020. Now, a perennial problem that's also an important extreme loading for infrastructure are earthquakes. And this may affect both buildings or highly populated areas, as shown in the top right, or again, our transport infrastructure, such as bridges and embankments in the bottom right. Now, these are global problems, and as such, you need global solutions. And over the past 15 years, we've developed quite a strong global network with the University of Dundee, and our international collaborators, academic institutions and industrial partners are shown on this slide. And you can see that they span 5 different continents. And I'd also, at this point, before I go forward and show some project examples, to say a big thank you to my various colleagues from the past years who have contributed to the projects I'm going to show. They are listed here, and they include academic staff, research postgraduate students, and also our technical staff. Now, technical staff are very important because all of the work I'm going to show revolves around our use of the Geotechnical Modelling laboratory at the university. So we're very lucky to have access to a centrifuge, that's shown in the image at the back, which is a device that allows us to take very large-scale real problems for big infrastructure and make a small-scale model that will have representative behaviour. This is the same concept as aircraft designers or racing car designers making small-scale models of planes or cars and testing them in a wind tunnel to obtain their behaviour. So if you like, the centrifuge is our civil engineering version of a wind tunnel. Now, as well as that, allowing us to test out new design concepts and provide data that we can use to validate new approaches. And we support that with computational modelling, as shown in the inset there, which allows us to help develop more sophisticated tools that engineers can use in practical design. Now, to move on to some project examples, I'm going to show a couple of examples in each of the areas I've talked about so far. So starting with the offshore storm loading scenario, we've done some work looking at high-performance anchors for marine renewable energy systems. Now, the project shown here is a case of, this was an EU-funded project focused on research for the benefit of small to medium-sized enterprises. So this is a funding scheme that allows companies that are otherwise perhaps too small, with not enough resources, to be able to come and access our facilities at the university to further their ideas. So in this case, we were looking at a drop embedment anchor that's shown in the picture on the right. The idea being this is much easier to install than current technology because we can take it out to the location we want to install it. We literally hang it off the side of the ship, let go, it will embed itself into the seabed like a dart, and then we can remove the bit that's shown painted in yellow, the follower that's just there to provide mass and embed the anchor, and we can bring that back to the surface and use it for the next installation. And the advantage of this is that we end up leaving a very small anchor, the black bit on the tip there, within the seabed. So it has a very high capacity compared to conventional anchors, perhaps 2 to 4 times the holding power per weight of anchor. So it's very efficient use of material. And combined with the fact that we can reuse the follower part, it means that we have a really very sustainable anchor solution. Now, we've also looked at some other types of anchor. This is an alternative, a screw anchor design here. That's shown in the inset diagram that's with the white lines. And this was developing an anchor that would carry load in a different way for much higher capacity applications. So in this case, a large offshore wind turbine. This was again some European funded work looking at this kind of screw anchor concept. This would replace a conventional pile anchor, which normally we'd have to hammer into the seabed, and that can be very detrimental in terms of the noise that creates to marine life. So the benefits of this anchor, it not only provides more capacity than the conventional anchor, but it also can be installed almost noiselessly, which is much better from an environmental perspective. So again, our role in this was again to develop design methodologies similar to the previous case, and develop simulation tools that engineers can use in practice, and to validate how they work and provide some confidence in them by testing these devices on the centrifuge. And in this case, we've since been able to take our anchor model and work with the Norwegian University of Science and Technology, as indicated there, to build our anchor model into a computational model, full computational model of an offshore wind turbine, which is shown in the image on the left. Now, moving on to the onshore problem, as I mentioned, this is a major problem for our transport infrastructure. So here we're looking at embankments and slopes and bridges. And this first example here looks at adapting aging embankments, perhaps from our Victorian industrial heritage, to be able to resist the more extreme weather we're likely to get with climate change, particularly heavy rainfall. So in this case, what we were looking at is the planting of vegetation. So rather than using a solution based on concrete or steel, to plant vegetation in a very careful way to make sure that the vegetation can remove water from the ground to give it more storage capacity. It can provide mechanical resistance to the slope to stop it slipping through the roots. And then by removing water after the event, it can reset the slope to its high storage capacity afterwards for the next event. Now, I've shown some centrifuge data as an example on the right-hand slide here. You can see in the upper image shows an untreated slope. This was subject to a failure. You can see the landslip shown by the black arrows marked there. The blue colours just indicate that there's lots of water in the slope. And this suffered a landslip after a sort of typical current heavy month of rainfall. In the bottom image, under the same rainfall scenario initially, we carefully planted some vegetation, and we were able to take this slope a lot further, continuing raining on it, and this was able to actually withstand more like a 1 in 10,000 year event that we might expect perhaps with climate change without failing. And the advantage of this is that it's a cheap solution, and it's also very sustainable. In addition to those benefits of not having a lot of embodied carbon from steel or concrete, it also provides that the above ground vegetation provides habitation to mitigate our biodiversity problem as well. Now, it's not just extreme rainfall that we have to worry about. We might get more extreme winters through climate change. And so here the problem may be snow and ice on our road network. So it's not necessarily so much the fact that our infrastructure will collapse or deform badly, but more that this will really badly affect the road users. So across a range of projects that were instituted by one of my former colleagues, and I was lucky enough to work on, we looked here at embedding geothermal energy systems within our infrastructure. So this might be within, say, the foundations of the bridge that you can see in the background of that image, or perhaps within the embankment slope you can see where the slip road is joining the motorway there. Now the concept here is we can access higher temperatures that remain deeper underground, bring those up to the surface and run them in pipework embedded within the road surface to de-ice the road potentially. Now, we're not suggesting this necessarily over a complete length of a road system, but perhaps at the areas where we have extensive accelerating and braking, perhaps at a grade-separated junction like this, to try and mitigate the hazard of snow and ice for road users as much as possible. Again, we spent a lot of time looking at how these systems work in the centrifuge and making sure that using them this way didn't affect their primary purpose to support the bridge or support the embankment, and also then based on that, to develop computational models that engineers could use in practice. Now, for the final problem, the final case of extreme loading I looked at was earthquakes. There are a number of projects I'm going to look at here. This first one looks at the design of novel foundations. So the image on the left shows some damage to a bridge in Japan following a major earthquake. Now we were able to replicate that in the centrifuge. You can see in the image on the top right, we have our scale model of this bridge, which using a type of model reinforced concrete that we uniquely developed here at Dundee. We were able to simulate the same type of failure, and then we can take that bridge and modify its foundations to come up with a better design. And we've worked with a number of different overseas partners testing out various different designs on this. The example shown here is with the National Technical University of Athens, looking at the concept of a rocking foundation. This is one where we can actually use a lot less material in the foundation. You can see the difference in size between the image in the bottom and the image at the top. By rocking around, it dissipates a lot of energy, and what we end up with is a foundation that can resist larger earthquakes using a lot less material, which is again very sustainable because it uses less concrete, less embodied carbon. Another thing we've been looking at is large, complex, interconnected systems. So these are things like lots of buildings being together in a densely populated urban area, or perhaps interconnected underground transport systems. Now there are two projects shown here. The first one on the left-hand side is an image from the Santiago Metro line, which I was fortunate to go and visit during its construction. Our role in this project, we're working with the University of Leeds and PUCV University in Chile. Our role was to look at the modelling of this system so that we could understand how this system behaves. It's a long tunnel with lots of interconnected stations, very complex system. Understand how it behaves so that we can then, the other partners could then go and install sensors into the system for measuring how it was going to behave moving forwards. We've now taken this modelling work forward a bit further. We're now working through the university's collaboration with the CMS, a detector in CERN in Switzerland. We are looking at assessing building a digital model of the big underground Large Hadron Collider, which again is a big long tunnel with multiple caverns for where the detectors are to detect things like the Higgs boson. And again, we're using this as another case study where we can further develop our methods of analysing underground infrastructure and make it resistant to earthquakes. So that's an overview of a range of projects that have been conducted here at Dundee. And obviously there may still be more work to do in those areas. I'm not saying that they're complete by any stretch of the imagination. But perhaps a final question is, where should we go from here? Now, in addition to those problems which exist on the Earth, one of the things we're going to be looking at in the coming years is moving away from the Earth and starting to think about potentially colonising the Moon and Mars. So this is really exciting because now civil engineers can start to have a real input into our humankind's development beyond our own planet. So we're currently involved in a project shown in the image here. We will need to build structures on these planets, and they need to be the structures we take there need to be protected from radiation, and that can be very expensive if we need to transport all of the material to do that as we travel there on a rocket. So instead, this project is one that was instigated by Foster & Partners, the famous architects, looking at using 3D printing technology to 3D print these domes that are shown in the image there as radiation shielding for these structures. Now, these are potentially very delicate structures, and they will need to withstand extreme loadings from asteroid impacts, distant and moonquakes, or Mars quakes if you prefer. And so we'll be using the centrifuge at the University of Dundee to both simulate the low gravity environments and using small scale models to be able to simulate how these types of structures will respond to earthquake loading. And we're doing that, hopefully civil engineering can contribute to both our further development on our own planet and our further development as we move beyond it.